We'll get started in a minute here. Let's see if she's not here yet. Doesn't mean we can't have class. It's just because there's one person. If you have any questions or things you want to talk about or have me talk about, just let me know. Yeah. Sure.
I think it's number 6. Yeah.
Which homework? The one, the current one?
Yeah, number 8. I did like half of homework 9 yesterday.
Okay.
And I was like,
right. Is that the ball one?
Yeah, it's the ball one.
Sure. Okay. Sure. What are your numbers?
Mine are, it's dropped to my 5 feet, and every time it bounces 0.87.
0.87?
Yeah.
That's a terrible number, but okay, great.
I mean, I didn't compute anything.
Right. Sure. So let's check it out. So ball is dropped from a height of 5 feet. I think I did this problem similar to this.
Unless it means that it check out the.
And
I might misread it. It might be losing points.
Okay. Certainly the way it's worded here, it says that's not the way I would read it.
No.
It rebounds up to 0.87 times the original height.
Times the height of the previous.
Right. Thank you. Yes. And the question is, what is the total vertical distance traveled by the ball? So if we let this go on literally forever, assuming we don't lose stuff because of friction, etc. So let's take a look. If we draw this picture here, the ball starts at a height of 5 feet, falls to the floor, and then rebounds up to a height of 0.87 times 5. So whatever that is, right? That height is 0.87 times 5. And then does it again. So that's going to be 0.87 squared times 5. And it keeps doing this and on and on and on. So what we're adding up here, and this is where we have to be a little bit careful, is we're starting off by adding the 5 feet it falls. But then it's going to bounce up this distance and fall this distance. So we're going to have not just 0.87 times 5, we're going to have twice 0.87 times 5. And the same deal here. This distance here plus this distance here is going to be twice 0.87 squared times 5. And twice 0.87 cubed times 5, and so on and so on and so on. So to me, what I would do if I was trying to calculate this is I would just break off the 5. Like I would think of that initial 5 as kind of not being important. And I would write this as 5 plus, from each of these remaining pieces, I can factor out a 10. So 5 plus 10 times 0.87 plus 0.87 squared plus 0.87 cubed, and on and on and on and on and on. We don't have to write this using sigma notation, but we could. You could write this as 5 plus 10 times the sum from n equals 1 to infinity of 0.87 to the nth power. But really, we know what to do here, right? This is going to equal 5 plus 10 times the sum of our geometric series, which should be the first term, which is 0.87, divided by 1 minus the ratio, which is 1 minus 0.87. So that's how we deal with most of that, I guess.
That goes-
Good. Were you missing the two?
Yeah, I was.
Cool. My eyes not feeling excellent. So it looks like in class today, you guys just continue talking about determining if a series is convergent or divergent using any of the tests, right?
Yeah.
The P series or the ratio test or a geometric series or nth term test. Right, exactly. So it seems to me like it would make sense to continue forward and start talking about what you're going to cover on class on Wednesday, right? Because we don't have class on Monday, just as a reminder, 3-day weekend. So let's kind of move forward and start talking about power series. So we're going to set this up in the following. Let's see. So we're going to back it up just for a second. So we're going to talk about power series, but just for a second, let's talk about geometric series for a moment. So for example, we know that this sum, 9 plus 3 plus 1 plus a third plus a ninth, forever and ever and ever, we could certainly find what that sums to. Again, we don't really need to write it as a geometric series, although you totally could. I know the sums to the first term over 1 minus the ratio, which is this, in this example is going to be 9 divided by 1 minus a third, which is equal to 9 divided by 2/3, which is 9 times 3/2, so 27 over 2. Similarly, we could say that 8 minus 4 plus 2 minus 1 plus a half minus a fourth. We do that forever. We could actually, I am gonna write this with the geometric series just to write it out. So it's the sum from n equals 0 to infinity of 8 times. What is my ratio here? Well, the easiest way to find the ratio is just to literally divide any term by its previous term. So we do like -4 divided by 8, that's going to be -1/2. Or even easier, -1 divided by 2. Oh yeah, that's -1/2. So my ratio here is definitely -1/2. And then this is going to sum to, since our ratio is between -1 and 1, the series converges, and it converges to the first term over 1 minus the ratio, which is going to be 8 divided by 3/2, which is going to be 16/3. So now the question I want to ask is, can we find a geometric series that sums to 10? Well, yes, we can. And what we're going to do is we're just going to kind of pick a starting place. So I'm going to say, well, I want something plus something plus something plus something plus something plus forever and ever and ever. I want that to equal 10. So I'm going to pick a factor of 10 just to make life easier. So I'm going to start with 2. And so I know that this geometric series, if it converges, I know I haven't written the terms yet, but if this geometric series converges, it's going to converge to 2 divided by 1 minus the ratio. So if I want that to equal 10, then I can just solve for r. So I can say 2 is equal to 10 times 1 minus r. 2 is equal to 10 minus 10r. 10r is equal to 8. R is equal to 8/10, which is 4/5. So I can say that my next term would be 2 times 4/5, which is 8/5. My next term would be 2 times 4/5 squared, and so on and so on and so on. 2 times 4/5 cubed, 2 times 4/5 to the fourth. So that I can say that my series looks like that. That I have the sum from n equals 0 to infinity of 2 times 4/5 to the n. And that certainly adds up to 10. Is that the only infinite series that adds up to 10? Definitely not. You could probably find literally an infinite number of different series that add up to 10, but this is one of them. But really the point of this is that we're going to ask the question, instead of finding a series that adds up to a specific number, what we really want to do is find a series that adds up to a specific function. And that's kind of where we're going with a power series. So the idea here is that we want to find a series that adds up or sums to the function f of x equal to 1 over 1 minus x. So we're going to use the same idea. We're going to say that we want something plus something plus something plus something forever and ever and ever to equal 1 over 1 minus x. Well, that looks pretty familiar. That looks a lot like a first term over a 1 minus a ratio. So it seems that our first term should be 1, and our ratio should be x. 1 plus x times x, plus x squared times x, plus x cubed times x, and so on and so on and so on. So it's true that this sum, the sum from n equals 0 to infinity of x to the n, which is 1 plus x squared plus x cubed forever and ever and ever, is equal to the function 1 over 1 minus x, with a caveat. So just like before, this geometric series, right, because it is geometric, every term is just the previous term multiplied by x. This geometric series only converges when the ratio is between -1 and 1. So this is true, or this converges, if and only if the ratio, which is x, is between -1 and 1. Or alternatively, we might write it as the absolute value of x is less than 1. The way we would say this is that this series, the sum from n equals 0 to infinity of x to the n equal to 1 over 1 minus x, has an interval of convergence, which is -1 to 1, exclusive of 1 and -1. And that's not something that's always true, right? Sometimes those endpoints get included, sometimes they don't. But we know that for a geometric series, the geometric series diverges if the ratio is either equal to 1 or equal to -1. So here we can just say, yeah. So this is kind of the idea of a power series, which is that you're adding up higher and higher powers of x. More generally, from way over there. So generally, I don't want to write this. Yeah, I want to write this. So an infinite series of the form, the sum from, n equal to 0 to infinity of a sub n times x to the n, where a sub n is just the coefficient and x to the n is just a power of x, which is a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed, and so on and so on and so on. This is called a power series in x. And just to be, just to be super kind of complete about this, there's also, and I should say, this one is centered at 0. And then even more generally, the sum from n equals 0 to infinity of an times x minus c to the nth power, which looks just like a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared plus a sub 3 times x minus c cubed, and so on and so on and so on, is a power series in x centered at c. The way I typically think of the center is that if you were to plug in x equal to the center, all of the terms, except for maybe the very first term, would end up equaling 0. By plugging in C for X, C for X, C for X, all those terms after that become 0, and you just get the initial term. So, some examples of power series. The sum from n equals 0 to infinity of x to the n over n factorial. It's a pretty popular one. We don't really need to write out terms, but if we were to write out terms, I will remind you that 0 factorial is equal to 1. So if I start writing out terms, my first term is x to the 0 over 0 factorial, which should just be written as 1, because x to the 0 is 1 and 0 factorial is 1. Plus x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on and so on and so on. Look, which, again, if I was writing it as a more typical person, I would write it as 1 plus x squared over. We usually don't write 2 factorial because 2 factorial is equal to 2, so it's often just rewritten as 2. But then 3 factorial, we do write as 3 factorial, right? We're not going to figure out what all of those are. The question arises is, for what values of x does this power series converge? So, question. What x values does this series converge? And almost always, the way we answer this question is by applying the ratio test. Which is what we're going to do. We're going to say, we're going to use the ratio test. So we're going to take the limit as n goes to infinity, a sub n plus 1 over a sub n. And here we do need those absolute values. I know I was omitting them when I was doing this before, but now we really do need them. So we're going to write this as the limit as n goes to infinity of our a sub n plus 1, which is going to be x to the n plus 1 or n plus 1 factorial, times the reciprocal of the a sub n term, which is just x is the reciprocal of x to the n over n factorial. So n factorial over x to the n. And then we're going to simplify this. So we're going to get the limit as n goes to infinity of the absolute value of x to the n plus 1 over x to the n, which will simplify to just x, times n factorial over n plus 1 factorial, which will simplify just to 1 over n plus 1. Let's write it out. The limit as n goes to infinity, the absolute value of x times n factorial over n plus 1 times n factorial. The n factorial is canceled. And we get the limit as n goes to infinity of the absolute value of x divided by n plus 1. Now, here's where we have to be a little bit careful. X is just representing some value. 5, it could be a billion, it could be negative 23, but it's some set number. And then we're taking the limit as n goes to infinity of some set number divided by something that's growing larger and larger and larger. So that limit is going to be 0. And then we have to remind ourselves, if we use the ratio test, the limit has to be less than 1 for the series to converge. But this limit is always less than 1, no matter what x is. So in this case, this is less than 1 for all values of x.
But the nth term test, doesn't that just tell us whether it diverges?
Right, but we're not using the nth term test. This is the ratio test. Right. So we'll do another example in a minute that I think will make things a little bit more clear. But here what we're saying is, for any value of x, the limit of the ratio test is less than 1. Meaning for any value of x, this series converges. So what we can say is that the sum from n equals 0 to infinity of x to the n over n factorial is convergent for all values of x. In other words, it converges on the interval negative infinity to infinity. Let's look at another example, one that's a little more exciting. Well, maybe not more exciting, more interesting. Let's say we have the following. Let's say we have the sum from n equals 1 to infinity of x minus 2 to the nth power divided by n squared times 3 to the n. I will point out, because I think it's worth pointing out, the center of this series is positive 2. And I can see that by saying, well, if I set x equal to positive 2, almost all the terms, I think all the terms are going to end up equaling 0. If I write this out, my first term is x minus 2 over 1 squared times 3 to the 1. My second term is x minus 2 squared over 2 squared times 3 squared, and so on and so on. I can see that if I set x equal to 2, all of those terms will end up being equal to 0. And that's how I usually identify the center. We'll see a little bit more about that in a minute. So, for what values of x does this series converge? Well, again, we're going to use the ratio test. No, actually, one. So I'm probably going to end up saying a little bit more than we usually say in this class, but that's okay. I think we can handle it. So we're going to use the ratio test. And this is always going to be what we use if we're trying to find the interval of convergence or the radius of convergence, which is actually what we're being asked to find. So the ratio test says we're going to have the limit, then goes to infinity, of my a sub n plus 1 over a sub n. Since the limit is then goes to infinity of the opposite value of. So okay, so let's see, my a sub n plus 1 is going to be x minus 2 to the n plus 1 over n plus 1 squared times 3 to the n plus 1 times the reciprocal of my initial thing, which is going to be n squared times 3 to the n over x minus 2 to the. Simplifying this a bit, all right, this is the limit as n goes to infinity. X minus 2 to the n plus 1 divided by x minus 2 to the n is just going to be an x minus 2. 3 to the n divided by 3 to the n plus 1 is going to give us a 3 in the denominator. And we're going to have to deal with the n squared over n plus 1 squared. If we want, we can rewrite that. Whereas the limit as n goes to infinity of the opposite value of x minus 2 over 3 times n over n plus 1 quantity squared. And as n goes to infinity, the limit of n over n plus 1 squared is going to be 1. So then we end up getting the absolute value of x minus 2 over 3, right? We've dealt with the limit. So the limit is kind of weirdly something that still has x in it, but that's typical for a power series. And now we're going to say, for this series to converge, the ratio test says that this limit has to be less than 1. So then, okay, so usually what I would do is I would actually go find the interval of convergence by solving for x, but no, I'm still going to do that here. But usually in this class, we only really ever ask about the radius of convergence. So, but let's solve for x here. So we have, I'll say that in just 1 minute, in less than a minute probably. So solving for x, we have x minus 2 over 3 is between 1 and negative 1. And then I'm going to isolate x. I'm going to multiply everything by 3. So negative 3 is between x minus 2 and x and positive 3. Sorry. Negative 3 is less than x minus 2 is less than 3. Finally, adding 2 to everything, we get negative 1 is less than x is less than 5. So here's what's happening. the interval of convergence is from -1 to 5. Now, the reason we don't really talk about the interval of convergence in this class is because technically you have to check the endpoints, because if this limit's equal to 1, the test is inconclusive, and so you have to like check x equal to 5 and x equal to -1, and it just becomes kind of more than we really are have the tools for. But if you look at this, check this out. So here's x equal to -1. Here's x equal to +5. And in the middle of -1 to 5 is, you guessed it, the center, which is 2. That's one reason we call it the center, is because it is quite literally the center of the interval of convergence for the series. And if you think about the center being like the center of a circle, well, then the distance from the center to either end is the radius. So this radius here is 3. So I would say that so I don't really want to say the interval of convergence, because I'm going to say the actual wrong thing. The interval of convergence we could think of as being from -1 to 5. And in this example, it actually does include the endpoints. I'm not going to say the wrong thing. I can't say the wrong thing. So the interval of convergence will be bracket -1 to bracket 5. But again, the endpoints are dicey. And then the radius of convergence is r equal to 3. Backing up a moment to the previous example, I know we didn't talk about it because it was going to be kind of weird, but here, if the interval of convergence is literally everything, then we say that the radius of convergence is infinity. So if the series converges for all values of x, the radius of convergence is infinite.
So if it only converged on 1, the radius of convergence would be 0.
Yes, and we'll see an example of that as well.
People may this, but what's the significance of the radius of convergence?
That's a good question. So the thing here is that this series is actually equal to a function, which we are not quite like. That's kind of like the next thing we talk about. But what we're going to say eventually is, I'm going to give you a function. Like I'm going to say, take sine of x. We want to write sine of x as a power series. So it's going to be kind of weird. It's going to be like sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, et cetera, et cetera, et cetera. There's a reason this is useful. It's useful because sometimes we just want to estimate like an integral of something that actually isn't integrable. And so we use its power series expansion to do that, or at least we use like the first maybe 10 terms and then cut it off. So we estimate the integral using a function that's easy to anti-differentiate. But then the interval of convergence says we're only allowed to do it for values of x in this interval. So that's why the interval of convergence is kind of important, because it limits when this equality is actually valid. So in this example, this power series, whatever function it's equal to it for every value of x. But in this example, this power series is only equal to its function when x is between -1 and 5. And outside of that, it's not a valid statement to say that this power series is equal to some other function. So that's why we talk about the interval of convergence, because you're only allowed to say that this is equal to this other thing when x is between, in this case, -1 and 5. That might not be the best answer to that question, but it's an answer. Yeah. What's the book say? I'm curious. Okay, sure. So they phrase it in maybe a better way. I kind of like the way they've written this. It's a word I should have thought of. They say that f of x equal to some power series from n equals 0 to infinity of a sub n times x minus c to the n converges. Actually, what they say, sorry, where the domain of your function is the values of x where the series converges. So basically, we're just defining the domain of the function. Yeah. So let's look at another example. Let's say we have the series from n equals 2 to infinity of n times, do I like that? No, I didn't like that. N factorial times x to the nth power. I don't really like this example that much, but it does show us something important. Yeah, that's fine. Okay, fine. No, I don't like that. I'm going to change it just slightly. I wish I could actually just change it, but I think I just will cross it out. I'm going to actually make it a slightly different. Apologies. We go from n equals 2 to infinity of n factorial times x plus 6 to the nth power. So I changed it from this one having a center of 0 to this one having a center of what? -6. The center, again, just the value you would pick for x that would make most of the terms easier. So let's find the radius of convergence. We're still going to, oh, I know what I want. Sorry, I want to back up 1 second here. I want to back up the previous example just a moment. So one thing that I've noticed over the years about the radius of convergence is that the radius of convergence is just the reciprocal of the absolute value of the coefficient of x. So if you look at this here, the coefficient of x is 1/3. So the reciprocal of 1/3 is 3. And that's true whether it's positive or negative. That's always true. So if you're trying to just identify the radius of convergence, you don't have to quite go as far as I've gone here.
So the radius of convergence would always be half of the distance between the two endpoints, right?
That's how I love to think of it. Yes,
So
exactly.
the diameter of convergence?
That you are spot on. So we don't usually talk about that, but you would be correct in saying that for this previous problem, the diameter of convergence is 6. For the one before that, the diameter of convergence is infinity. And so then the radius is infinity divided by 2, which is still infinity. Here the radius is 6 divided by 2, which is 3. And I think that's a great way of finding the radius of convergence. That's how I usually prefer to do it. But looking at this next one here, we're going to do it again. So we're going to take the limit. We're going to use the ratio test. So it's all about the ratio test when you're finding these radii of convergence. So limit n goes to infinity, absolute value of the an plus 1 over an. You can skip writing this step. I just like writing it to remind myself of what I'm actually doing. So it's going to be the limit as n goes to infinity of n plus 1 factorial times x plus 6 to the n plus 1 divided by n factorial times x plus 6 to the n. We're going to simplify. So the limit as n goes to infinity. N plus 1 factorial divided by n factorial is just n plus 1. And x plus 6 to the n plus 1 divided by x plus 6 to the n is just x plus 6. Okay, so here we have to be a little bit extra careful. 2 different things can happen. Thing 1, if x happens to equal -6, then we have the limit as n goes to infinity of the absolute value of n plus 1 times -6 plus 6. But that's 0. And n, before I take the limit, n is just a number. So 0 times anything that's finite is 0. So this is the limit as n goes to infinity of 0. The limit of a constant is just the constant. And that is less than 1. So if x happens to equal -6, this limit is 0, the series converges. But if x is equal to anything else, then we have the limit as n goes to infinity of the absolute value of n plus 1 times x plus 6. X plus 6 isn't 0. it might be really small, but it's not zero. And any non-zero number multiplied by something that's getting infinitely large is going to get infinitely large or negatively infinitely large if it's a negative number. And then the absolute value of that is going to be infinity. So for any other choice of x, this limit is infinitely large, which is certainly larger than 1, which means we get divergence. So for this example, the interval of convergence is literally a single point. So if I was going to graphically see this, and there's my center at -6, and there's my interval of convergence, just the point there. You won't typically be asked to write this, but if you were, you would say the interval of convergence is the set containing just the single value -6. But the radius of convergence, well, my interval has no length. The length is 0, the radius is 0. So we kind of classify the options for the radius convergence as 3 possibilities. Either your radius is 0 in a situation like this, your radius is infinity in the first situation we had, or your radius is some actual real finite number. Those are the 3 things that can happen when you're finding the radius of convergence. So let's look at another example. Let's say we have the sum from n equals 0 to infinity of -1 to the n times x minus 3 to the n over, sure, 2 to the n times n plus 3 to the 4th. That's fine. That's fine. Okay. So, usual stuff. We want to find the radius of convergence. And so I'm going to try and do this problem by showing as little work as at least by not showing too much work. I'm going to try to show as little work as possible. So I'm still going to start off with the ratio test. Limit and goes to infinity. Absolute value. Okay, this is going to be a little bit gross here. -1 to the n plus 1. X minus 3 to the n plus 1. Over 2 to the n plus 1 times n plus 1 plus 3 is n plus 4 to the 4th. Multiply by the reciprocal of all that. So 2 to the n times n plus 3 to the 4th over -1 to the n times x minus 3 to the n. Combine the things. So let's see here. The -1 to the n plus 1 divided by -1 to the n is just a -1. The x minus 3 to the n plus 1 divided by x minus 3 to the n is just an x minus 3. The 2 to the n divided by 2 to the n plus 1 is a 2 in the denominator. And then the n plus 3 to the 4th and the n plus 4 to the 4th, we have to kind of put together. You have n plus 3 over n plus 4 to the 4th. The real truth is that the polynomial things in these, like if you have an n plus 3 or an n squared plus 1, those really don't end up having any effect on the overall limit. So we're going to get the limit as n goes to infinity of this n plus 3 over n plus 4 is going to go to, not surprisingly, 1. And we're going to get the absolute value of -1 times x minus 3 over 2. Now let me ask you, if I was to do more work and multiply this out, what would the coefficient of x be? Correct. We don't really care about the negative sign though, so, but you're not wrong. I wanted you to say the negative sign. So observing that the coefficient of x is -1/2, the radius is the absolute value of the reciprocal of that. So my radius of convergence is going to be the absolute value of the reciprocal of the coefficient of x, which is just going to be 2. You could do more work, right? We could say, oh yeah, this needs to be less than 1. And then you could say, great, -1 over 2 times x minus 3 is between 1 and -1. And then you can multiply everything by -2 and get 2 bigger than x minus 3, bigger than -2. And then you could add 3 to everything and get 2 plus 3 is 5, bigger than x, bigger than -2 plus 3 is 1. And oh, look, the diameter of convergence is 5 minus 1, which is 4. So the radius of convergence is 4 divided by 2, which is 2.
We could just find one of the endpoints of convergence and then use the radius to find the other.
Totally. Yeah, that works too. Typically in the 60, so if you look in the textbook here, they don't really talk about the interval of convergence at all. They really just talk about the radius of convergence because, again, they're really trying to avoid the issue of determining convergence at the endpoints. Because to determine convergence at the endpoints, we typically have to use something called the alternating series test, which we don't talk about in this class. So that's why we're kind of avoiding the issue in general. Yeah. What do you think? Should we do one more thing or should we call it a day? Okay. So here's what's coming. So the reason we're talking about these power series is because what we're really doing is we're building up to something called Taylor's formula or Taylor series or Maclaurin and the light version of that's Maclaurin series or Maclaurin's formula. So a Taylor series is just the way you take a function and write it as a, oh yeah, I just remembered there's a really good video about this. It's kind of like, I think it's like 15 minutes long, but there's a great video explaining like why the Taylor formula works the way it does and also kind of why it's useful. It's kind of neat. I will find it and post it on Canvas because I think it's super useful, or at least it's nice to be like, oh yeah, this kind of makes sense. But the idea is that Taylor's formula allows us to find the power series for almost any function. Let me show you an example, and yeah. So here's an example. F of x equal to e to the x. That's a function that's clearly not a polynomial, right? It looks like this. It's for sure not. Oh, I'm going to show you something cool. Yeah. Okay. So what we do here is, and I'm just going to show you the formula right now, and then maybe next class we'll talk about how it's derived. But here's the formula for Taylor's formula. So Taylor's formula says that f of x is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at your center. We call C. That's what the book says, right? Yeah, the book uses C. Good. Some books use A for the center. Divided by n factorial times x minus c to the nth power.
What's the center?
Well, we get to this. Well, I will say usually it's given to you. So in this case, we're gonna find the I feel like I'm saying the wrong words here. Yeah, we're gonna find the Taylor series for f of x equal to e to the x centered at c equal to 0. 0, by the way, if the center is 0, it is also called a Maclaurin series. But that's really just because like the guy Maclaurin did it for the center being 0, and then the guy Taylor was like, oh, we can generalize this to even other places. So yeah. If they say Maclaurin series, the center is 0, but you could just as easily say a Taylor series center is 0. All right, so this one is really nice because we're going to find a bunch of derivatives of our function, but you know what? If our function is e to the x, the first derivative is e to the x. The second derivative is e to the x. All the derivatives are e to the x. And if we plug in our center, which is 0, all of these are going to be just 1. So f of 0 is e to the 0, which is 1. And f prime of 0 is e to the 0, which is 1. All the way down to the nth derivative at 0 is going to be e to the 0, which is 1. So when I write this out, what this tells me is that my function e to the x is equal to the sum from n equals 0 to infinity of the nth derivative at 0, that's just 1 every time, divided by n factorial times x minus 0 to the nth power, which is a series we looked at before. That was the first thing. And also, and just because it's cool, the radius of convergence here, we already saw, was infinity. So it's kind of interestingly true that e to the x can be expressed as this infinite series, e to the x equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial forever and ever and ever. And that is true for any value of x. It's kind of great. Now, here's what I think is kind of cool. Sometimes we use a Taylor series, but we only go up to like I could use the 7th degree Taylor series, which means I'd be stopping at x to the 7th power. And I might use that to approximate, well, I say we can use a Taylor series later on to approximate something like e to the x squared. And the reason that's useful is because e to the x squared is a function that cannot be integrated. So I can use the Taylor approximation of it to approximate its integral, which is super useful. Maybe super useful might be an overstatement, but useful nonetheless. But here's what I want to show you, which I think is kind of cool. And then we'll call it a day. So, check this. Here's e to the x. And what I'm going to do is I'm going to start graphing the Taylor series. So watch this. So, okay, not very interesting so far. There's the first, so there's the Taylor, I should say, that's the Taylor series of degree 0. I've just done the very first term, which is x to the 0th power. And I will note that the Taylor series and the original function should always agree, mean have the same y value at the center. And they do. When x is 0 here, both my Taylor series and my function have a value of 1. And now I'm going to add on the next term. Hey, look, that's a bit of a better approximation, at least close to the center. And when x is 0, I still have both functions equaling 1. And then I'm going to add on the next term. So now if I add on the next term, oops, careful, James. It's an even better approximation. And the more terms we add on, the further and further away from the middle, the approximation continues to be good. So if we add on the next term, x cubed divided by 3 factorial, which is 6, even better. And you could, and literally, I mean, you could do this forever. Well, couldn't because we're out of time, but right, the more terms you add on, the better, or I should say, the larger the interval of being a good approximation exists. And so if you could do this forever, the approximation would literally be exactly the e to the x function, which I just think is neat. Like that is cool that if you just keep adding on these terms, this polynomial thing gets really, really close to being e to the x. And the other thing I want to show you, which is another way that we actually know this is e to the x, is what's special about e to the x, kind of compared to any other function, is that it's its own derivative. Well, look at this. If you take the derivative of this expression, you take the derivative of 1 plus x plus 1/2 times x squared plus 1 over 3 factorial times x cubed, and so on and so on and so on. Look what happens. The derivative of 1 is 0. The derivative of x is 1. The derivative of 1/2 x squared is 1/2 times 2x to the first. The derivative of 1 over 3 factorial x cubed is 1 over 3 factorial times 3x squared. 1 over 4 factorial times 4x cubed. But 1/2 times 2x is x. 3 factorial is 3 times 2 times 1. The 3's cancel, and you get 1 over 2 factorial times x squared. Same deal here. 4 factorial is 4 times 3 times 2 times 1. The 4's cancel, and you get 1 over 3 factorial times x cubed, and so on and so on. It's exactly the same. So taking the derivative of this yielded the function we started with, which is just more evidence that this really is the function e to the x, because only e to the x is its own derivative. All right, that's all I have to say. We'll talk more about this next week on Wednesday. It is really cool.